Alright, good morning. Today we're going to see how we can use triangle similarity to solve a problem like this where we have a right triangle ABC and its altitude BD and find a few missing sides. So the directions say to find BC and DC given that AD equals 3, BD equals 4, and AB equals 5. Now, if you notice in this problem, there are three distinct triangles: ABC, ADB, and BDC. And sometimes when we're doing these problems, it helps to separate the triangles into separate pieces. So for example, if I draw a triangle like this, and I can claim that this is a right angle and that it's going to represent the triangle DAB. This triangle on the left here, DAB. Well, how do I know it has a right angle there? Well, because on a straight line is 180, there's a right angle here, therefore this must also be a right angle. Well, how do I know where to put my numbers? Well, if we look at AD, that has a measure of 3, so I can put it right here. AB, our hypotenuse, has a measure of 5, and DB has a measure of 4. So that is one of the separated triangles. Now we can draw another triangle. How about similar path, just like this, keep it the same sort of format, and I'm going to claim that this is D at the point of the right angle, and then I have B over here and then C over here, and I know that BD is 4. That is the only thing I can conclude so far about that triangle. And then finally we have the whole triangle that is not going to be drawn to scale, but you should get the idea that this is ABC, or BAC, which has a length AB of 5, and that is it. So, how can I use this information to find BC? Let's say we're finding BC first. Well, I know that all these triangles must be similar. Why? Because, for example, ADB and ABC both have a 90-degree angle, and they both share the angle A, right here and right here. So ADB is similar to ABC. In addition, I know that BDC is similar to ABC because they both share an angle at C, and they both have a 90-degree angle. And if ADB is similar to ABC and ABC is similar to BDC, then ADB must also be similar to BDC. This is the transitive property. Therefore, I can justify making proportions and ratios based on the side lengths of these triangles. And I know that each ratio should come out equal to another corresponding ratio. Therefore, I ask myself, what side would BC correspond with? Well, BC is in our triangle ABC, and it also is in our triangle BDC. I can pick either of these two triangles to work with. I will pick BDC. Now, BDC has BC as its hypotenuse. How can I tell? Well, the hypotenuse is always across from the right angle. So now I have to pick another triangle's hypotenuse to create a ratio. Well, if we notice ABC, we do not know what the length of the hypotenuse is, so I cannot use that. However, in ADB, I know that the hypotenuse has a length of 5, so therefore I can write a 5 below like that. Now I must create another proportion, or another ratio I should say, that would cause a proportion. Since we started with the blue triangle in the first ratio, we have to start with the blue triangle again in the second ratio. So what else can I use? Well, I have the number 4 here, and because I'm trying to solve for BC, I don't want any other variables or missing side lengths. I want numbers, so I'm going to put the side that equals 4 there. Now that is the side BD, and I went from the blue triangle to the triangle ADB. Now which side matches up with BD? Well, if we notice, AD is going to match up with that side. They're both the smallest side on their respective triangles. So BD matches with AD, therefore we have 4 over 3. And if I multiply the 5 over to the other side, we will get that BC is equal to 20 over 3. And that is one of the sides that we need to solve this problem. Well, then I have to ask myself, how can I find DC? We're going to start out with DC, pick a triangle to work with. I can pick the blue triangle again and look at this side DC. Well, what side would that match up with? Well, if I look at ADB again, that would match up with DB, 4. And I must set that equal to, and I can use the same ratio we used for BC, the 4 over 3, because I know that that is consistent. Multiply the 4 times the 4, and we will get that DC is equal to 16 over 3. And that is that missing side. And that is how you can solve a problem involving similar triangles with right angles.